This is the 4.4 and 4.7 review. Calculators are not allowed. This will be a multiple choice problem. However, you don't have a calculator, so that means you're going to have to go through all of the process in order to find. The only thing you won't have to do is the justification. So I will verbalize the justification on each of these just so that you kind of have a feel for how it'll work. But you're going to have to set up your model, take your derivative, etc. So if we look at part A, it says if y equals 3x minus 6, what is the minimum value of the product x, y? So the question is, what is the minimum value of the product? So when we're done, we're going to want the minimum product. We're not going to quit until we have that. To get there, we're going to create a model or a function for the thing we're trying to minimize. The thing we're trying to minimize is that product. So that's P, and we want it to be in terms of x only. So right now the product is an x times a y. I need that y to be in terms of x, and fortunately they gave it to me right here. For ease of derivatives, I'm going to multiply that out since I don't have a calculator to help me with the derivative. And now I'm ready to take the derivative because I cannot minimize and maximize things until I identify the critical values. When I take the derivative, I get a 6x minus 6. I'm interested in when that equals 0 or undefined. It's never undefined. It's 0 when x is 1. So now to analyze whether or not that's the location of a minimum, I will need to do a sign chart. And notice I did not get any domain limitations, so my domain will be all reals or negative infinity to infinity. So that means all I'm going to put on here is this 1. If I look prior to 1, say it's 0, and I plug it into the derivative, I get a negative value. If I look after 1, say at 2, I'll get a positive. So I can see that because P is continuous and P prime is changing from negative to positive, that P has a minimum at 1. So P has a min at x equals 1, which means we have found the location of the minimum. So in order to find the minimum product, I need to plug 1 into the product function. When I do that, I get a 3 times a 1 squared minus a 6 times a 1. That gives me a 3 minus a 6, or a negative 3. So my minimum product is negative 3. If we look at part B, it says I've got a box with a square base and no top, and I need to hold 32 inches cubed. So I just gave you information about the shape and the volume of that shape. My goal is to find the dimensions that require the least building material. So what I want are the dimensions when I'm done. So I'm not finished until I've set up or answered the question about what the dimensions are. So I've got a square base. I'm going to draw this picture. A box with a square base and no top. So I have a choice here. I can choose to let x be the height, or I can choose to let x be the base. And I'm going to choose the base because I'll get more bang for my buck. I get 2 x's on that instead of just 1. And then I'll let my height be an h. So the things that we know are that the volume, which is the base times the width times the height, or x squared h, is going to be 32. I'm going to utilize this to help me get my surface area, which is the building material, to be the least amount. So currently my surface area will be the bottom, which is x squared, plus the 4 sides, because I don't have a top. Now each side is going to be an h times an x, and I've got 4 of those. Now my goal is to use the least building material. So that means it's the surface area that I need to minimize. That means it's the surface area that I need to have in terms of x. So if I look here, I can see that I need to get rid of that h. Well, fortunately up here I've got a formula that I can use. If I isolate h, I'll get a 32 over an x squared. So my surface area is now x squared plus 4x times a 32 over an x squared. Now because I don't have a calculator, I'm going to have to take the derivative of this thing by hand. So I'm going to simplify it first and get an x squared plus, let's see, one of the x's will cancel, and on top I'll have a what is that, 128. So here's what I need to take the derivative of, and let's think about the domain. We know that x can shrink as small as we want, close to 0. And then if we look at h shrinking, that would mean h would be 0, but that's never going to happen because x can never get large enough to create an h equals 0. So that means my domain will just be 0 is less than x, or x is greater than 0. So now I'm ready to take my derivative. Derivative of this one is a 2x. This is the same as a 128 times x to the negative 1, so that would be a negative 128 times an x to the negative 2. Or, because I know I need this to equal 0 or undefined, I'm going to rewrite it as a 128 over an x squared. And then I'm going to get a common denominator. This needs an x squared, so I'll have a 2x cubed minus a 128 over an x squared. I need that to equal 0 or undefined. Well, it's undefined when x equals 0, but that's not in my domain. And it's 0 when x cubed equals 64, or when x equals 4. So if I now analyze my sign chart for s prime, domain starts at 0. I've got a critical value at 4. Prior to 4, say at 2, this number will be smaller than the 128, so I'll end up with a negative on the top followed by a positive. So I do have a minimum when x is 4. If this were a free response, I could say s is minimized when x equals 4 because s is continuous on its domain, and s prime changes from negative to positive. Now, because we have found the location of the minimum, now we need to go and figure out what the dimensions are. So the dimensions of a box are the length, or the base length, width, and height. So x is 4, so we've got a 4 inches by a 4 inches by, now we need the height. Well, the height is 32 divided by that 4 squared. So 32 divided by 16 gives me 2 inches.